Agrawal, CEO of Lambda Labs. So this is a presentation on Monday, March 22nd from the San Francisco Bay Area ACM, or Association of Computing Machinery. Welcome, everybody. A little bit of background about the San Francisco Bay Area ACM. So we were founded in 1957. We're focused on promoting knowledge of modern computing. Want to create community, support networking and hiring. $20 is an annual membership. Our local chapter would be separate from National ACM. We have upcoming talks on our meetup site, the SF Bay ACM, and we have about 185 plus or past talks on our YouTube channel. Also search for SF Bay ACM. We have 2 monthly meetings. General computing talk is typically the 3rd Wednesday of the month, and a data science SIG is typically the 4th Monday of the month. We have a joint meeting schedule. We work with other societies such as IEEE and ValleyML.ai. Talking about our upcoming events, we have in April, lessons and opportunities in large-scale networks and smart health application. So if you have any questions and answers, go ahead and do that through the chat function of Zoom. So a little bit of background into the talk, seeing exponential growth in compute requirements for state-of-the-art deep learning, such as the Microsoft has a Turing natural language generation model with 1.7 billion weights. OpenAI's GPT-3 has 175 billion parameters. Designing an optimal AI infrastructure is becoming as important as designing better DL models for an organization. So this discussion will include a description of the infrastructure choices available for deep learning. The infrastructure setups are trying to keep up with the computing requirements. A little background about Mitesh. Lambda Labs is an AI infrastructure company with a background in chemical and hardware engineering. A founding team member is worked on building deep learning for early startups to Fortune 100s for Lambda's, and also for Lambda's GPU cloud setup. You can see more at lambdalabs.com, or I'm also listing the LinkedIn profile for Mitesh. You can check that out as well. So now we can switch over to our speaker. I'll stop sharing.
Thanks, Greg, and thank you everyone for joining, and thank you SF Bay for getting me on here. I'm really happy, and then it's always fun to talk any kind of infrastructure for me. I'll start off with saying that as you might have seen, and there was a famous paper that kind of suggested that over the past decade, kind of the growth in deep learning has come mostly from kind of hardware and compute improvements rather than model optimizations. Although I do not fully adhere to that, but it does show the importance of understanding the computing architecture in terms of really increasing your machine learning, deep learning model speeds, optimizing them, and actually just getting faster output and faster time to results. So yeah, that's why I personally think along with there are a lot of kind of talks and everything that is coming up within the ML engineering world, both from model side as well as hardware side. I think it's very important to keep on point for both of them because sometimes what cannot be solved with model optimization can just be solved with hardware or compute optimization, and can reduce your training time from let's say days or months to few hours, and so literally a multifold increase, which can be, depending on the cost and everything, it can be worth it for your organization. And I think today that's what we're going to kind of get a little bit of deep dive into. I'm going to attempt to kind of discuss the thought process that goes behind building a cluster at any of these companies who are building on-premise hardware for themselves, or are actually using cloud, whichever it might be. And hopefully the session is kind of a good, you get a good insight into what goes into thinking about kind of a computing cluster for doing deep learning, and what's happening, or what's currently the state of the art in the world. I'm going to start sharing my screen. Please let me know if you have any technical difficulties in seeing my screen. Greg, can you see my screen?
Yes, I can see your screen.
Perfect. Awesome. Yeah, Greg already gave me a great intro, and thanks again for that, Greg. Really appreciate that. So the quick thing is, I'm part of the company called Lambda Labs. We are basically a deep learning infrastructure company which provides turnkey GPU cluster solutions, as well as we put a software layer on top of it to make it easy to manage. We call that product called Lambda Echelon. It's basically a fully rack stack labeled, cabled cluster of compute, networking, storage, power, et cetera, setup that we provide. We also have our own cloud infrastructure, again, solely targeted toward the niche of machine learning and deep learning. Our cloud is basically a GPU cloud infrastructure setup that is, built first and foremost, keeping in mind deep learning applications, you name it, CNNs, NLP models, anything such as those. And we try to basically provide the fastest kind of throughput there with our architecture, as well as one of the main mottos of our company is trying to provide kind of maximum flops per dollar. And that's what we try to achieve both with our on-premise solution as well as our cloud solution. One very quick intro. Also, to everyone, please feel free to ask questions, as you feel at any point of time. Happy to discuss anything, even if it's not on the topic, if I know the answer. But in 2012, it's one of my favorite papers, of course, and one of the, I believe, truly like a Kickstarter for GPU, which are the graphical processing unit. NVIDIA and AMD basically are the two major companies that make those. But for deep learning to really get a boost in terms of what happened in compute was this 2012 paper by Alex, Ilya, and Jeff Hinton, pretty famous names. Ilya now works at OpenAI. Jeff Hinton, considered the father of machine learning. They published a paper, and they used at that point of time NVIDIA GPUs called GTX 580, which only had 3 GB of memory on them. For their ImageNet results, and they kind of published the benchmark results, and it kind of blew away the existing benchmarks that were being done on CPU compute nodes or anything such as that. And one of the main reasons is, in terms of computation, machine learning is what we call parallel computation. So GPUs are kind of designed for that. NVIDIA, maybe by accident or by exactly knowing what they were doing, figured out that GPUs were a perfect use case for a machine learning or deep learning application. Initially they were designed for video rendering and gaming use cases, especially the GeForce GTX 580 series. But once they realized that, they have come out with a really solid array of products, as well as software support in terms of everyone uses TensorFlow, PyTorch for writing their models. That's built on CUDA libraries and NVIDIA's GPU drivers, and then they've really come out trumps there in terms of providing that support. So that's how kind of this started, where GPUs started becoming the go-to for hardware compute. And as Greg mentioned in his introduction, the Microsoft's model has 1.7 billion parameters, and the new, GPT-3 was all the craze in 2020. I remember. And people are still, it's still an amazing model, but it has 175 billion parameters. As you can imagine, the scale of the infrastructure needed to train these models is off the charts right now. So people, and especially various companies, may that be startups, all the autonomous driving companies, or Fortune 100 companies who are getting into language processing, such as Microsoft and Google, Teslas of the world who are into, CNNs. They all, build their own GPU clusters, or they run large-scale cloud deployments. Netflix is a big example of running cloud deployment. So it's very important to kind of see that, all these companies are going towards larger and larger deep learning infrastructure solutions. Deploying in data centers or running in cloud with AWSs of the world. So it's really good knowledge to know how these companies approach this process and how these clusters are built and how can they improve basically, their lead times and everything. GPT-3 model, for example, it wouldn't have been possible to train that. OpenAI has a deal with Microsoft to run huge V100 GPU clusters, and that, without those many, hundreds and hundreds of GPUs, it's almost impossible to run GPT-3 in any kind of reasonable time frame. So it's, it's not just the GPUs that are important, it's what it goes around that as well. The storage part of it, the networking is very important because people get bottlenecked on networking. So I think I'm going to try and cover some of the aspects there.
Just as an analogy, it's like you can have a sports car or a race car with a great engine, and if the rest of the car isn't tuned, if you don't have huge wheels to get the traction, if you don't have everything else to handle the bandwidth, you're limited by your weakest link of the chain, so to speak, in the whole system. So as a comment.
Yeah, that is a spot on. No, Greg, I'm going to start using that. Actually, that is exactly correct in terms of how, and that's why building a cluster is not as, it's not just racking up some servers, it's also understanding the networking topology, the communication channels that all the CPUs, GPUs, memory, and storage are using, and such that you get optimized results and actually get the best bang for your buck in terms of output. As I said in this slide, I mentioned that there are two ways that companies usually scale their solution. One is they build their own GPU cluster. The second is they run large-scale cloud deployments. Almost every company, I'll be honest, starts off kind of, on either with the cloud credits when they're startups, or what they do is they start off kind of slow and low, basically one server or one workstation with a few GPUs, and then they scale up to this. Why companies do on-premise or like they build their own is there's definitely one big aspect of data sovereignty and security. Healthcare companies, insurance companies, you can imagine, for example, would not want their data on the cloud, and so they build their own cluster. Another is if you have a huge amount of data sets and you do a lot of egress from AWS. If you have dealt with cloud builds, that it's not actually the compute costs which are killers, it's actually the data ingress and egress costs which can really build up your bills. So that's another reason. And just, by nature, cloud makes it very easy to use it, but it's also an expensive, whereas having an on-prem setup, it gives you more compute for a dollar, but of course you have to think around managing and upkeeping it. So if you have an infrastructure set up already in your company, it's a lot better, or it depends on the perspective, but it's a lot cheaper to do on-prem. Whereas if you want to scale up quickly and you want more ease of use, then cloud is the way to go. Basically, the biggest thing is scaling. Like if you're doing an inference application, for example, like you're running a company like Uber, and you scale up, your compute requirements literally scale up with the number of users logging into your app. You want quick scaling up abilities, and that's where the cloud really comes into play and really comes into its own. I always look to, I don't have any other rule, so I don't know why I label it in the rule number one, but basically, when you are trying to build a cluster, the most important thing to know, and the only rule to know, is kind of know your machine learning team or know your machine learning application. As you probably have heard, machine learning can be divided into two main things, training and inference. Training the models, and then inference is kind of the production deployment. And within training, there is kind of, hyperparameter search that kind of finds the best model that gives you the best output for whatever your application is. And then once you've figured out the best model, kind of scaling it up to a large-scale distributed model. And I think Greg mentioned the next talk is on large-scale networks. So you will kind of see, I think they will touch upon how they started out with finding the best model and the best fit, and then kind of expanding that model to train on multiple nodes and multiple GPUs. So as I said, finding the best model, it's kind of referred to as hyperparameter search. Then once you've found the best model, you want to shorten the time to convergence, or time to train. and that's achieved by large-scale distributed training. So going from example from 1 GPU to 4 GPUs to 8 GPUs to 64 GPUs and so on as per the resources and everything of your company. And then once the model is trained, of course, deploying this model at production for your end users and end customers to utilize, and that's labeled as production inference. So the cluster design is usually kind of influenced. So this is the kind of the main summary of this presentation. If anything to take away from is understanding what your use case is, and then understanding the deployment of your cluster. This is just a quick question, but like basically, which neural network we think would perform best? Of course, it will be one with the most layers and most nodes. So the answer will be B. So if you run basically a neural network with kind of a topology as set up like this, you'll get different accuracy levels. Most people prefer to maximize the accuracies. So, this is where the hyperparameter search kind of comes into play, where you're kind of running different types of model, and it truly is trial and error. People just add weights, people add nodes, people add multiple layers, and you try to find as much of an accuracy with as small a model as possible, because you want to optimize for compute. So people are just running this locally on their kind of local machines, maybe a laptop, maybe a desktop, maybe a workstation kind of setup, just to see whether the model works or not. And then once you've figured out the correct model, you see that, okay, this model will take on my small experimental machine, it will take 2 days, it will take 1 month, it will take, multiple months. Then starts the process of trying to figure out, how do I make it faster? How do I make it run faster? As I said, most people, start with experimental, like on a laptop or a workstation, and then people go into the servers. Now, servers are not something you would put kind of in your own house. They're just too loud and everything, unless you're doing, nowadays people actually have put servers to do mining and stuff like that, utilizing their laundry's output and everything, like, the power outlet. But usually servers go in places like server clusters, or kind of a server closet, or ultimately into data centers. These are like, rackable machines with a huge amount of compute power within each machine, as well as when you combine them together, you get a lot of CPUs, the traditional compute, GPUs, which are the used for deep learning, lots of RAM and memory, and also lots of storage. You're talking about scale of multiple terabytes to multiple petabytes of storage. But what happens is as people scale their models from 1 GPU to multiple GPUs, especially nowadays, it's so much easier. The code change to go from 1 GPU model to like an 8 GPU model is a single line command in PyTorch or TensorFlow. It's all native. Like in TensorFlow and PyTorch automatically figure out that you have multiple GPUs, and they can deploy the model on multiple GPUs. So because it's so easy, people scale up their models quite easily, and they can either run the same job on multiple GPUs, or you can run multiple jobs on the same machine. It equates to kind of similar things, that you're just kind of scaling up your infrastructure there. It's just a quick illustration to show that, if you're running one model and you're running it across multiple servers, it's a quick, Microsoft Paint job. But basically, the big difficulty comes in not actually the software part of it. I'll be honest, scaling up, as I said, it's so easy with well, not to say easy, not to trivialize it, but it's already well documented in terms of how to scale up your model. You have the TensorFlow PyTorch to scale up from within a single node from 1 GPU to multiple GPUs. Then you have the Kubernetes kind of layer, along with a lot of tools to help you with kind of go from a single node to multiple node in terms of doing distributed training. Uber released like kind of plug and play, like Harvard, which allows you to again scale from one node to multiple nodes, or one server to multiple servers. But the difficulty comes in actually managing these nodes, interconnecting these nodes, figuring out power for this, figuring out that there's no bottleneck for the data input into the servers. No matter how many GPUs you have, if your storage cluster cannot keep up in providing the data to this, then your GPUs are just sitting idle. So you have spent all this money on GPUs, which are generally the most expensive part of a cluster, and it's just sitting idle, pretty much doing nothing there. And then, as I said, it requires lots of server-to-server communication, which automatically implies high-speed networking. So you need all of the parts here for a cluster to perform. And then eventually you go into production inference, where once the model is trained, then you have this end users pinging you from their devices to, like, for example, if you're doing a translation service, then they're typing hello in their translation app, in your translation app, and your server has to run the AI model and then feed back the results. So you're basically running multiple instances of the same model and multiple users at the same time. There you're having to deploy multiple servers, and you have to basically prioritize the queries. If you have a paid service, of course, you have to prioritize the paid service members first in terms of processing queue, and then if you have a free, freemium service, you have to process them later. So that all that arrangement will have to go into this. Now, again, to remind you, as I said, there are two main things. People can do on-premise installation, or people can do cloud. For inference, people prefer cloud because they want to take away the lead time lag. When you're doing on-prem, you have to place an order for servers. You have to deploy them. You have to make them come online. But if a user growth suddenly happens from 10,000 to like 100,000 users, you do not have that much time. So, and on cloud, you can just run multiple instances and scale that up. And then it also allows you flexibility because, let's say, maybe Saturdays and Sundays are very busy for you if you have a delivery service, but Monday to Friday are not. And you go from 10,000 users to 100,000 users back to 20,000 users. You want to scale your compute accordingly. You don't want to be stuck with a cluster which supports 100,000 users and not using it. So cloud allows for that, and that's where the inference come into play. But if you have a more uniform distribution of requests, then absolutely on-prem still makes sense because it's more bang for your buck there. This is just a quick summary that I do in my day-to-day job. Actually, when I'm discussing clusters with engineering teams or with data center teams, kind of what are the main metrics that they need to kind of consider. And I'll be honest, the first metric everyone looks at is price, and I've written it in the middle. But it is very important to know kind of what is the price parameter if you're doing an on-prem cluster, and it's with hyperparameter search, if let's say you're an early stage startup, you're just figuring it out as to what type of model is suitable for my application. There is no need to spend your hard raised dollars that you've just raised in seed or Series A into a distributed training network or inference kind of cluster. There's no point in running, getting huge 100 gig networking cluster or very high speed storage. All you need are a few GPUs to start training and to figuring out, run your hyperparameter scoring and figuring out what's the best model as well as what's the ultimate GPU for me. And that could involve just buying one machine or one server or one workstation, or even if it's multiple, you can just connect it with your usual 1 gigabit or 10 gigabit network because you're usually not running large scale distributed training. And there's no point in spending multiple thousands of dollars on a large scale distributed training. It might be just better to start off with a few $1,000 machine. And that's why it's important to understand what stage you're at. And a lot of times, startup companies get their cloud credits. Once you run out the cloud credits, you realize that cloud can be very expensive to do hyperparameter search because you're paying for kind of premium instances, and you're paying for all the bells and whistles that you don't need on a cloud. For example, on cloud setup, you have all the networking, 40 GB or 100 GB networking, very high kind of memory or very high kind of storage setup. You a lot of times don't need that, but you're paying for those bells and whistles even though you don't need it. So it might be important to consider that, maybe I'll just buy like a local machine, which will help me figure out the correct model. And you can buy multiple workstations for your engineering team, and that will help them kind of just quickly figure out the right model, and then you're ready to deploy it on cloud or your on-prem cluster, however you see fit. Whenever you're doing kind of a deployment on infrastructure side, there are 3 levels of abstraction. The biggest one is the cluster. Of course, you hear and you see these images, and if you've seen the show Silicon Valley, they show you this data center racked with kind of multiple racks of servers and machines that are just running and humming away using tons of power and everything like that. So that's the cluster. Then a cluster is collection of multiple racks, and a rack is collection of multiple nodes or servers or rack units, as we call them. So it's important to start from the node when you're building up a cluster, because it's important to understand what are all the components that you kind of need there in terms of your GPUs, in terms of your storage, in terms of your networking and everything like that. Combining those and putting wiring and connecting those builds up a rack, and then powering those racks builds up a cluster across different racks. And these racks will be nothing without software. You need that's the biggest actually challenge, is kind of doing software deployment, which allows you to quickly deploy your models across these multiple racks. And if you have multiple users, you have 8 users, you have 15 users, you have 100 users in your company, how can they easily spin up a GPU on your own on-prem cluster? Basically, having your own on-prem cluster, but doing it as an experience of cloud. The biggest aspect, as I said, of cloud, if you go to Lambda Cloud or even AWS Cloud, is how easy it is to spin it up. You just basically sign in, you put in your credit card, and you have a GPU instance ready to run your machine learning model. And you want your kind of on-prem cluster to have similar experience for your internal engineering folks. And that's where this deployment software kind of comes into play. As I mentioned, the cluster part of it, by the way, this is like a rack, just as a quick photo. You have your GPU servers, which are, at the bottom, there's like a 10U GPU server. It has 16 GPUs. Then you have kind of the power supply unit in the middle or on the sides, depending on how much power is needed. Then you have other 4U servers, and the U's are the kind of the length of the servers in the rack. So, you have the 4U, which are like the medium 7 to 8 GPUs. And then at the top, you have the networking switches. You can probably see those red cables at the top. Those are the networking ports that are used to connect all of the servers and talking to each other. And then you have multiple of these racks kind of getting built. As I said, just reiterating the point, there's a lot of aspects that go into building a machine learning infrastructure. Starts from just building your compute and storage and networking nodes. And then comes the power part of it, how much power is needed to power on these servers and figuring that out. And I put in colo, and colo stands for co-location or data center, because when you're going into data center mode, most people, most companies are probably putting it in co-location services or data center services, where they're racking up these racks. Very few companies would put this in their own office or in their own WeWorks or in their own kind of closet space. There are some companies, if when they have infrastructure engineers and they have enough power, they do put it that, because it is, of course, again, far cheaper to run your own than putting in a data center. But more often than not, people put it in data centers that are run by a third party. You might have heard of Equinix or Digital Realty or Colavor or Scale Metrics, or big companies like Facebook and Google and Teslas of the world build their own data centers, because they just have that much compute requirements. And that kind of combines into the deep learning infrastructure. I did forget the software piece there here when I was making the slide. So another part that goes into it is software. I did write it here though. Basically what all goes into it. It's just a reiteration. But within software, as I said, there are terminology called cluster orchestration, job scheduling, resource allocation. What I mean by that is basically, you have multiple engineers running their models, and you have a finite amount of computing resources. So you want to allow them to, you don't want them to wait until a GPU is available to basically release their code to the infrastructure. You basically want to say, all right, whenever you're working, maybe 2 a.m., 2 p.m., whatever time they're working at, just release your code, and whenever the GPU resource becomes available, it'll run that code. And that's what kind of a job scheduling or resource allocation is. And then of course, you want environment control. As many of you might have run your models, you know that there is a certain version of TensorFlow you need, or certain version of PyTorch you need, which is compatible with certain version of CUDA, or certain version of a specific model type. And you need that kind of container, so that every single time an engineer is spinning up an instance, they can bring up their own container. This was Mitesh's environment that I set up, an Anaconda or Docker or whatever that is. And that becomes very important to do fast and optimize training jobs. So those are kind of the software that you need to think about when you're thinking about cluster design. And these actually, I know I'm talking about in large scale clusters, and a lot of folks might not need to ever design this or anything, but just knowing these aspects will help. I truly believe will help even in your kind of local machines and local models, because when you're planning out your model, you kind of think about, okay, how am I going to scale it up from 1 GPU to 4 GPU to 8 GPU to multiple GPU application, and this will really help there. You want to optimize for maximum GPU utilization, because when you grow at a single GPU, utilizing GPU at 70% or 80% or 100% doesn't really make a big difference in how much it's costing you to run it. But when you're scaling that over 100 GPUs, think about all the power cost if you're not utilizing your GPU to the fullest, and how much more extra money that you'll be spending there. Or if you're running it on cloud, think about how many more GPU instances you'll have to run if you're not optimizing your model to full 100% utilization of the GPU. So it's very important to run kind of, this hardware protocols or command, like, NVIDIA-SMI, or you're running Slurm to see, if your kind of nodes are being fully utilized or optimized.
There was a question from Dave. How much power in watts per rack can most co-location facilities handle today?
Awesome question. I think I have it in my slide later on, but I do want to answer that actually. So there is this now kind of a two design portfolio in the data centers that we see. So as you know, traditionally, AWS clusters, Amazon, Google clusters, they were designed around, kind of your e-commerce use cases or web design or anything like that. So these were CPU or storage clusters, and they used to use less power. CPU uses 250 watts of power, and there are only like 2 or 4 CPUs per node, and there are like 20 nodes in a cluster or so. So these racks were 10 kilowatts, designed for those kind of thing. Storage drives, for example, almost use next to nothing power. So the old school data centers were designed for 10 kilowatt to 15 kilowatt rack power consumption, and that's what their provision is. But with GPUs, with this high density GPU servers, kind of the game has changed. This 15 kilowatts, each server, like each 4U server, is using anywhere from 3 to 4 kilowatts of power, and you can rack 10 of those in a single rack. So now your use cases require you to have 30 to 40 kilowatts of power in rack. And the new data centers that are coming up with liquid cooling or rear door exchanger, they support up to 50 to 60 kW. In fact, I was working with the data center, and they're designing an 80 kilowatt rack density because this new, you might have heard of this A100 GPUs by NVIDIA, or they are like super power hungry GPUs, each GPU using 350 watts, and each server having 8 of those GPUs. That server is using 4 or 5 kilowatts per server. So you're now needing 50, 60 kilowatts per rack. So as I said, there's this clear distinction between GPU racks now, which use 30 to 60 kilowatts, and this old, kind of this storage and CPU compute rack, which are 10 to 15 kilowatt. And hopefully that helps you understand kind of, if you're designing a GPU cluster, you need to figure out a 215, 220 volt, 3-phase power with 30 amps to at least provide 17 kilowatts in a single rack to power on and have enough density so that you're not just wasting space and rack space. And the biggest thing is actually not the space is not expensive, it's the networking which is expensive. If you if you're just filling up your rack, like, 1/4 of the way or 1/3 of the way because you don't have enough power, and then you're just doing multiple racks, you have to think about networking. You have to have multiple switches in each rack, top of the rack switches. You have to have those cable lengths, and you have to expand those. And that's just an added expense that you would have avoided if you just packed them all in a single rack and only have one networking top of the rack switch connecting all of those. So hopefully that explains why power is important, and why it's important to think about this while you're designing the cluster, and why it's important to choose your data center as well. If you're just running storage cluster, absolutely, 10 kW, 15 kW per rack, go for it. If you're designing a GPU cluster, you need to talk to your data center folks saying, hey, what can be done to do, 17 kW or 20 kW, 30 kW, so that I can actually do a dense rack within a single rack and not expand to multiple racks for no reason. Any other questions?
Oh, just the dense racks are so much more important because when you have the GPUs located so close together, the bandwidth is so much higher, right?
Yeah, that's exactly, and that comes from networking, as I mentioned. If you're running 100 gig bandwidth requirements between the servers, or 200 gig nowadays, or the A100 servers support up to 1600 gigs between each server, the shorter the cable lengths are, the lower latency you have, and the lower cost. These cables are like, multiple hundreds of dollars. The switches are multiple thousands of dollars. So the lesser the amount you use, the better it is. The more you can, if you have the money, the more you can spend then on compute, which is what is driving your use case, rather than on networking and everything like that. And the lower the latency, of course, the faster the bandwidth there is, which are exactly the questions these three are kind of thinking about. How much compute do you need? How fast do you want the computer to talk to each other? And how fast do you want the computer to talk to be able to storage? Because again, you don't want your GPU sitting idle. You want your bottleneck to be the GPUs. You don't want your bottleneck to be your networking, to be your storage, to be your power. You want to utilize all of the GPUs, all of the GPU power, because that's where you spend the money on. So that's where you need to utilize all of those, and that's what you need to optimize for. This is just a quick storage, as I mentioned quickly, and there are so many storage options that it is very, very important to think about, what type of storage you need. Like, just to give you an example, right? Like, for example, if you're running a language processing, natural language processing model. Now, natural language processing model by its own nature tend to be very communication intensive and requires huge amounts of data. Because this is just text data, the GPUs process them very quickly. So you have to basically have huge amounts of data fed into GPUs. And you need very, very fast networking and very fast storage to feed that amount of data into the GPU, so that they are not bottlenecked on the storage data that it's being fed into. So here you need NVMe drives, the volatile SSDs, basically, which have very, very fast data transfer speeds. You need 100 gig or 200 gig networking setup, either Ethernet or InfiniBand, so that you're actually utilizing the GPUs. But let's say if you're running an ImageNet model, and I'm not saying this is completely across the board true, there are of course always exceptions, but let's say you're running a CNN, yeah, there is a data requirement, but actually you're more bottlenecked on the GPUs processing the images and actually doing the identification or classification or object identification, whatever model you're running. And it's not more about the data transfer, it's more about the GPU compute that is bottlenecking you. Then you don't need to spend so much on NVMe drives, or even if you want, you can do a hybrid. You can do NVMEs as your kind of hot drives, or your kind of temporary drive where the data is sitting. But if you just for storing, data, because video data is very, very huge. When, for example, when Tesla is collecting all of this road data, like all the video data, they have huge amounts of petabytes, and they're letting it sit on HDDs, which are the cheaper drives. But because they don't need that data right away for training, they only need some subset of it. And then they bring that subset over to NVMe, and then they bring that over to the GPU cluster. So again, very important to think about these things when you are kind of designing your storage cluster, because you can really optimize for cost here and really, really get huge amount of flops per dollar here. This is the kind of the same logic as I said, when you're designing your GPU setup, you want to optimize for latency. The lower the latency, the better it is for your models. So you want your data to directly reach the GPUs because that's where the compute is happening. The CPUs are not playing a part in most deep learning models, unless you're doing kind of data pre-processing or reinforcement learning models. And it's very important to understand topology of the server you're buying. So like, when you talk to your server vendor, or when you're going on an AWS instance, look at the type of instance you're spinning up. Like, if you're spinning up an V100 instance, then you know that your whatever data you're feeding is directly communicating to GPU. It has a huge amount. It has very low latency. It's going straight from NVMe drive to the GPUs. But if you're spinning up, like, for example, like a old P100 or K80, that's going through from drives to CPU to GPUs. So not only are these GPUs slower, but they're also causing a little bit more latency. Again, if you're doing kind of just a model experimentation, it doesn't really matter. Choose the cheap instance because you're just trying to figure out what the best model is. But if you're running production level instances, then it might be worthwhile to go for expensive V100, because even though they're expensive, you might be getting more throughput. Your throughput has increased multiple fold, and your cost has only increased a few fold times. So it's important to understand kind of the topology. And of course, I didn't want to bombard you with a lot of information on what different types of topologies. I do have slides here later, but basically, you can look up PCI topology. That's usually the term that is used. And feel free to contact, me or companies such as Lambda Labs, where I work, or, whoever your vendor is, maybe Dell or HPE or whoever that is, in asking them, hey, can you show us the PCI topology? Can you explain, when we are designing this cluster, how the data is going to flow through? That's very important. So that was about storage. The second big thing that you're trying to avoid networking, bottleneck on is your InfiniBand or your networking or your Ethernet networking connection. So here, I just have designed a quick kind of cluster and broke it down into how it looks in terms of networking cables. As you can see, networking is I believe it's the most complicated part of a cluster design after software and after software setup. At least with software, once it's installed, you can do whatever you want with it. You can change it if it's not something you like. But with networking, the cost to change is very, very high. Once you have determined it and once you have applied it, if it doesn't work and if you're still seeing bottlenecks, the cost to change is massive. And forget about all the time delays and everything like that. So it's very important to design networking from scratch when you're designing a cluster. As you can see here, you need to have enough ports to support, like, let's say right now you're only buying 2 servers, but you want that rack to expand to 8 servers in the future. You don't want your networking switch such that it only supports 2 servers right now. You want enough ports such that without adding more switches, you can just support that further. And this is not upselling you. This is just for networking. It makes sense to have as little of ports, as little of networking switches as possible, because the switches are the more expensive parts. Adding more switches adds more complexity, because then you have to connect one switch to another switch for all the servers to interact. Whereas if all the servers are going into one switch, then you don't have to worry about all the servers interacting with each other, because the switch is handling that. So it's always better to design around having a switch setup which allows for multiple server expansion. Even within switches, there are multiple types. As I mentioned, if you're running language processing models, if you're running doing large-scale distributed training networks, you need high networking bandwidth. You need 100 gigabit per second, 200 gigabit per second setups, which is nowadays with PCIe Gen 4 is now feasible. So you need the InfiniBand or Ethernet 200 gigabit setup. But for your kind of what is called out of band management network, where you're just kind of maintaining this, when you have multiple servers, you look at the status of the servers. Is the server healthy? Are all the fans running fine? Are all the GPUs running fine? You don't need to spend there you don't need high networking bandwidth to know that. That's just a continuous piece of information, which takes very little amount of data. So you need like 1 gigabit per second kind of Ethernet network. And you don't need to spend on a multiple $1,000 200 gigabit per second switch. You can make do with 1 gigabit per second, which is a few $100s. So again, knowing all of this, connecting all this by cables is very important. So again, when you're discussing it with, when you're designing it either internally or discussing it with your cluster provider, or if you're spinning up a whole cluster on cloud instance, ask them about, how is the networking topology connected? Whether I have direct access from NVMe, my storage to my GPU server using 100 gig or 200 gig InfiniBand or kind of networking setup, or is it just your normal 10 gig setup? Because if you're doing large scale distributed models using Horvath, or you're doing natural language processing model, that 10 gig is going to be bottleneck. So no matter how many GPU instances you buy on cloud, or how many GPU nodes you buy for your on-prem, if your networking is just 10 gig, you're not actually using them to full extent. Your GPUs are just sitting idle waiting for the data to come in. So again, it's important to ask these questions and understand kind of what the topology there is. This slide I just put in because if you're designing, if any of you is either so lucky or so unfortunate, whichever way it is you look at it, are designing your own data center or own kind of full rack stack, a label cable, multiple solution out there. This is what kind of, is very important to understand kind of how far are the racks, what is the power that the question asked is how much power can your data center provide? What PDUs are provided? Is it the 220 volt? Can they accept 3-phase power, or is it 415 volt, 60 amp? Setup. What are the power connectors that you will need? Those are all the decisions that go into it. What is the floor plan? What is the maximum cable length that you'll need to connect all these different servers who will be in different racks? So it's very, very important to think about this design. That this is what goes into kind of data center designs and everything like that. So it's very important if you want to learn this. By the way, if any of you is in kind of machine learning, if you're an ML software engineer or kind of researcher, generally you don't need to deal with this because we're getting taken care of. But if you are like an ML engineer or ML infrastructure engineer, or kind of getting into HPC, HPC space, if you know this gives you a big leg up on like if you're talking to a vendor like Lambda or someone like Dell, if you know these things, then you know exactly what to ask for, and it gives you a big leg up in your negotiations. Also within your own setup or infrastructure setup, it gives you a big technical knowledge boost in terms of designing your cluster. When NVIDIA comes out with a paper that they design a cluster with 96 servers, this is exactly what they're saying. They're designing this multiple racks and optimizing it for large scale models. So when you're doing it for either your own company's use case or your own startup's use case, as you build your company, or you're designing it for some other company, it's very important to just even know the terminology. Just power setup, PDUs and everything like that is very, very useful in knowing that. Finally, and this is a very important slide, so I don't know if you can take a screenshot or something. Please do. As I said, software is the most important piece to run all of these. Eventually, you can put up as much hardware as you want, but if you don't have management software on it, it's useless. It's so much of a hassle. Then this is why people choose cloud, by the way. One of the main reasons why people choose cloud is they don't want to do this. They don't want to figure out the software. They don't want to put efforts. They don't have the infrastructure admin to do all of this. But companies who do want to do this, because there's huge cost savings in rolling out your own on-premise, have to figure out this thing. So there are these software tools which are absolutely needed to make your cluster run smoothly and to make your on-prem cluster feel like a cloud environment. It ranges from kind of your training management software. So if you're familiar with machine learning models, you might have heard of companies such as Weights and Biases or Determined.ai or Spell.ml or Comet.ml. These are kind of like, what GitHub is to normal code. These are kind of like these repositories for ML code where they help you do version control, but they also have added parameters. They show you how optimized your model is, whether your model is running, utilizing the hardware at full, full optim, like at full 100% utilization, whether your parameters are optimized. You might have read about different papers, like the kind of a lot of parameters are just useless parameters in machine learning models. You don't need those. I'm forgetting the name of the paper right now, but very famous paper came out last year, which was named the NeurIPS paper of the year, where they show that kind of just if you just set up, if you just reinitialize all your parameters to zeros and ones, which is basically giving it no weight, it doesn't affect your accuracy of the model at all, almost, very little, because a lot of weights are just not needed for your model to run optimized. And that's what this experiment management software does. Of course, you need like a lot of researchers are used to like certain kind of interactive, like a Jupyter Lab or IPython notebook kind of setup. So you'll need that across all your instances. You need containers, Docker, where, as I said, to maintain CUDA version, TensorFlow version, PyTorch version, because you can't have one production version. And then when you're going into deployment, you can't have another version. That is a recipe for disaster in terms of deployment. I guarantee you that. So you need Docker to maintain kind of these containers, and you need containers to maintain these versionings. Kubernetes to manage instances and execute containers. Job schedulers I mentioned earlier, so that if you have multiple researchers, you basically track them and have, so that they can just they can just write their code, put it in the queue, go get their coffee, do whatever they want, so that they don't have to worry that, I have to constantly be on the lookout for GPU availability and push my code. Logging, which is the obvious thing. When you're going inference, then you need that production level software, TensorFlow or Serving or TensorRT to manage that, to figure out number of users and how to scale up accordingly. And then Lambda Labs, where I work, just as a quick kind of input here, we provide like a Lambda Stack software, which is a Debian repository. You can imagine if you have done any kind of TensorFlow upgrade or PyTorch upgrade, how much of a pain it is to figure out dependencies. TensorFlow is dependent on CUDA, on a version of CUDA, which is dependent on some certain version of cuDNN. So you have to manage all this upgrade. You have to do them in a certain order. With Lambda Stack, for example, a solution like Lambda Stack, which is a Debian repo which works on Ubuntu, you basically run a single line command, sudo apt get upgrade Lambda Stack, and it will do all that management for you, where it will upgrade all of CUDA, cuDNN, TensorFlow, PyTorch to all of the proper kind of interdependent versions there, all the GPU drivers and everything like that. So having something like that really helps across all the servers, because then you can run a sudo apt upgrade command across all the servers, and that you have the same version control across all the servers. So again, this is just a more visualized setup of how like the software stack will look like. Operating system, you use your base level. Then you have the drivers, the system libraries like cuDNN, Nickel. You have your developer tools, Vim, curl, whatever you prefer, IPython. And then the machine learning frameworks, these are specific to machine learning models, TensorFlow, PyTorch, Keras. Now they're all rolled into PyTorch, and then, of course, the Docker containers and the system-wide installation. We have more information on our website, by the way, all of this. There's a very good white paper called Lambda Echelon. It has all of this information. So if you might be wondering, hey, I'm saying that you need to know this, or it is good to know this, where can I find this information? Lambda has compiled this into a very good white paper setup, and you can read that. And it's just an interesting read if you want. There are also lots of public resources on Google where you can go.
A question for me: Does it have things like Onyx to transfer from PyTorch to TensorFlow or OpenVINO?
So Lambda Stack itself doesn't have that capability, Greg, right now. Okay. So you'll have to install that on your kind of environment on like a sudo install if it's on Ubuntu on its own. But yeah, so for conversion such as that, if we don't currently Lambda stack doesn't have it, but that's actually a very good suggestion. I had never thought of that, that people convert. Yeah. So
Okay.
that's actually a very good suggestion. Yeah.
Minor comment. Thanks.
Yeah. No, it's good to know. Again, just a full-blooded view of how a rack looks like. It's, I just wanted to show off. We spent we took a nice photo and then showing, but this is kind of how like a rack cluster looks like. Look at this. This is a very, very dense cluster. You can almost see no gaps. The only gaps you see are this, I don't know, like from the top, if you see this black kind of panel, that's a gap just given between the networking and some of the clusters. But this has like storage setup, this has GPU cluster, this has networking switch, and everything, like all the cabling is done on the back side of it. And this is a very dense cluster. This requires 30 kW of power to run it. And then this is kind of like, again, just to a sales plug or whatever you want to call it, this is like a Lambda designs this cluster fully rack stack label cable integrated and kind of delivers it to the end customer, or we have our own co-location service where we can spin it up for you if you're doing your own cluster. But this is also how it looks like in an AWS data center, a GPU data center that is out there. Some version of this, they have different designs, but kind of how it looks like. This is just like a more in-depth design, all the components that go into it. Again, kind of like and I just use the Lambda products for now, but you could replace it with any product that you have of any company that you wish to put in there. But you have the rack, you have the compute nodes, which is the CPU, GPU nodes, you have the storage node, you have the PDUs, you have the networking switches, and then you have the kind of top of the rack management switch going into a single rack. This is a standalone rack. This rack can be a fully utilized standalone rack. If you're doing multiple racks, then you can put networking on one rack. You can just stack everything with compute on one rack and things like that. So multiple racks can be designed differently. This is when we are doing kind of an engineering process or sales engineering process with you on a sales side. I just wanted to give you kind of an insight into, we design like an Excel spreadsheet, with kind of the servers and everything that goes into it. We just design a quick back of the envelope setup so that we know exactly which in a rack where exactly which server is set up. So I just wanted to kind of show some images that kind of go into it. I think Dave asked the question about power draw, and that this is why bill of materials is so important. So if ever you're designing your own rack or you're asking kind of vendors to design, discuss with them the bill of materials, because this is where like knowing the TDP draw, that's the total power draw basically, knowing. So, as I said, this rack that we designed has a total power draw of 36.95 kW. So you really need high density rack solutions for this rack to work on its own. But again, these are the processes that go into play. As I said, the most important number is the total rack TDP there. So this was about cluster. I know it's not, I apologize if this topic was not exactly kind of like suitable. I know it's not every day that you design a rack. It's not, most researchers don't design a rack, but I just wanted to kind of give you an insight that goes into this infrastructure setups that actually powers these models. And as I mentioned, a huge amount of what has happened in the past 10 years in terms of machine learning development and you see AI, it's not just a buzzword anymore. People actually using AI tools within their application. The huge amount of it comes from this hardware or appliance kind of increment rather than model optimization. I know like the Mascar CNN or ImageNet models are old models, but they're still used. YOLO models, the difference between version 3 or YOLO 3 or YOLO 4, very little. So the models, they're not to say they're not, new models are not being developed and not being optimized, but a lot of companies still depend on the same models that were being used 3-4 years ago. But it's actually the compute which has gone up and the setup that which has been optimized, which has allowed for people to take further the next steps in deep learning and machine learning models and deploy faster and faster and faster models out there. The main reason why GPT-3 is possible is, I mean, I haven't looked at the code because they haven't released it, but it's not because of, they're just increasing parameters, right? I mean, and again, I'm not trivializing GPT-3. It's an amazing engineering and research feat. Like what OpenAI has done is fantastic there. But in essence, what they've done is they've increased the number of parameters from GPT-2, which just means that they needed more compute, which just means that they needed this cluster optimization or cloud optimization that Microsoft has provided them for running GPT-3. So GPT-3 is only possible because of this optimization that is coming in compute side of things.
Are you seeing much happening with much higher resolution images? Because I know the original ImageNet competition was 224 by 224, and going to a 640 by 480 camera without downsampling. But I mean, a minimum resolution to recognize a person and all the attributes on them, it might be 100 pixels. 100 pixels out of 480 versus 100 pixels out of an 8 megapixel image, where they can be 3% the height of the image. You can cover many more people that are farther away in the same image. Yep. But to go from a 640 by 480 to like even a 6 megapixel camera, maybe like 28 times more pixels. So and that's just the first layer of your network.
Yeah.
Are you seeing that in other clients starting to work with?
Absolutely. I mean, without disclosing the client, I am personally involved in a project where basically the name of the game is going as high a resolution as possible. You can realize, Greg, that this is very important in media and entertainment industry or image recognition, that are all the models that are coming through. You mentioned high resolution, you can do a lot more with a single image, but also it comes at a compute cost, right? So you want to have, you mentioned if you're doing 100 pixel on a lower resolution image or on a higher resolution image, now you can do way more images if you're doing at a lower resolution images. So you can, with the same amount of cluster, you can run a lot more images. But if your cluster design is optimized and you use the right GPUs, even if you go to higher resolution, because your compute has been like basically artificially increased through hardware, now you can do the same amount of images in the same amount of time while actually increasing the resolution as well. So one of the main reasons why people spend on more and more compute is actually on the image side is not running bigger models, it's actually increasing the image resolutions. So on language processing side, it's running bigger models. On image side, it's actually running higher and higher model resolution. You can think of, companies utilizing drones. You can think of companies doing kind of, store, data labeling. You can think of, kind of doing all these companies. They have higher and higher resolution images that they need to resolve to improve their kind of model performance. And that's where kind of optimization from hardware compute comes through. And the main thing that comes into this is actually I have talked all this about cluster and setups and infrastructure. The crux of all of this is GPUs. You're running your model on GPUs, and you want to use the best GPU out there. So in terms of, as I said, flops per dollar. NVIDIA has different levels of GPUs. They call, they have the enterprise GPUs like the A100, which is their top of the line, $11,000, $12,000 GPU. Then they have the RTX A6000, which they call it the visualization line. Like they market it more for rendering and stuff like that. The A6000. Then they have their gaming GPUs, like the 3090s, the 3080s, the 3070s that you're seeing nowadays. So it's very important to know what GPUs do you need. I mean, of course, we all like to, from a selling perspective, NVIDIA and Lambda and Dell, we all want you to buy A100, but does it make sense to spend $12,000 when you're just starting out with an experimentation of a beginning server? I mean, honestly, this can run well on 3070 or 3080. Like if your model fits in a 10 gig or a 20 gig kind of RAM, VRAM setup, and if you're just beginning, if you have a workstation setup, just try running it on 3080 and figure out whether the model is giving out the output that you want. And it will give you really good understanding of what your model does for $1,000 or $600. Not right now. I know 3080s are very expensive because of miners, but just going off of MSRP, these are a few $100 to $1,000 GPU rather than multiple $1,000 GPUs. So you can start with that, and then when you're building out a cluster, then you might be thinking, okay, what is the performance difference between A100 and 3080? And I don't know if
the 3080s and 3090s have been pulled from the market by NVIDIA, right?
So they have been pulled in sense of, Greg, in terms of the server GPUs. So NVIDIA does not want, so they have the UL, they do not want these gaming GPUs in servers. So basically what they've pulled is the server versions of these GPUs, but the gaming versions, the ones that go in desktops, the ones that are big and broad and have RGB lighting on them, they are still available. It's just that there is a huge shortage of them right now in the market. So that you might have noticed that if you go on eBay right now or Amazon, people are selling this for ridiculous amounts. 3x the prices that their prices is, just because of the shortage there. But yeah, the 3080s, these gaming cards have been completely pulled for server usage. NVIDIA does not want this going into data centers and everything like that. And it makes sense because these gaming GPUs are not server level enterprise GPUs. NVIDIA designs this A100 and A6000s for those use cases. And I will say this, with the new line, for example, A100, this can be anywhere from 3x to 6x faster than like a 3080 card, for example. And when you're scaling out a large scale deployment, that might be that speed gain is very much worth it. But again, like if you're starting out and if it's a single node or it's a single workstation, for example, personally, when I run I'm not a great machine learning researcher by any means, but when my team is running some kind of experimental model, or when I'm learning things, I don't want to, and I don't need to spend 30 grand on like a workstation. I'm happy with like a $6,000 or $7,000 or even like lesser value workstation just to learn experimental model. Like a $2,000 or $3,000 laptop could do me good if I'm starting to learn. If you're at a stage where you do multiple GPUs, or if you're doing like a bigger model, like a 2x 3080 or 2x 3090 solution could be a great solution for us, or for you to begin training your models. Even within your engineering team, like let's say you have a startup, right? And you just have like 4 or 5 engineers who are just running experimental models right now. Just buying 3 or 4 desktops or a single kind of server node with like kind of a, A6000 GPU or a Quadro GPU, could be a very good solution and could be a very good performance per price solution, rather than going straight up A100. But when you're scaling out for production, then the A100s make sense because these GPUs are going to last for 7-8 years. I mean, NVIDIA generally recommends 3 to 4 years, but just think of it this way: the P100 GPUs, they're still running, and they're 7 years old. The V100 GPUs, they're like almost 5 years old now, and they're still running and supported. So when you're talking about software support in the future, and when you're putting in like so much money into a cluster, that's where A100 GPU makes really sense, because this will be supported for a long time. These are designed for very high uptime. These are designed for server use cases. These are designed for that. So that's kind of where the discussion comes into play of using what type of GPU. And of course, if you just need a Ferrari, which is what an A100 is, and if you have the capability to buy a Ferrari, and because it's worth it for you in terms of how much speed increase it gives you, buy an A100. No problem. That's the best GPU out there in the market right now, bar none in terms of absolute performance. But is it the best GPU performance per dollar? It depends on the model. It really does. Like if you're just doing a single GPU model, and if you're doing image models, it's not the best performance per dollar GPU. Sometimes a 3090 could outperform in terms of performance per dollar or flops per dollar an A100. But if you're doing a language model, yeah, A100 is probably one of the best performance per dollar GPUs out there, even on a single GPU model, because it has 40 gigs of memory, so you can put a lot bigger model. The FP16 processing on it, which is what is used in language models most of the time, or mixed precision is very, like, it has a huge increase over 3090 or 3080. So yeah, that's like a 6x to 10x performance increase. So that's worthwhile there. So it really depends on the models. And you should, that's where, by the way, Lambda's, again, a little bit plug up for Lambda. That's where Lambda's expertise comes in terms of providing that information. We work within deep learning. We are deep learning researchers. We actually know, we actually have our benchmarks, which we detail for all GPUs, name like gaming GPUs, 3080, 3090, enterprise GPUs, 30, A6000, A100, your Titans, your Quadros, everything is out there. And then MLPerf is also like a more like general performance setup out there. Also, Greg, I just quickly want to check how am I doing on time, and what else? Like I have more things that I can talk about, but just wanted to quickly check here.
Yeah, you're fine on time. I mean, it's 8:10, 8:30 is reasonable to wrap it up. So, but if
Sounds
you need to go a little bit longer or stop sooner, that's fine too.
No, this is pretty late for most people, so I'm happy to wrap it up. And generally, I tend to find that talks more than 80, 90 minutes, kind of people zone out. So it's good, but there's a lot of resources out there. Lambda has the blog. I would say, like, personally, and you might scoff at it, but like, Reddit's RML, or like, Hacker News ML setup, or ML channels provide a lot of great materials, a lot of great open source information. The more knowledge you have, the more power you have in terms of designing your own cluster, understanding, I will tell you this, like, we have like deep learning research. I'm not a PhD, or I'm not a deep learning researcher, but we have deep learning researchers at Lambda. And when they did their research, they were focused on models and software only, and a little bit of code optimization. When they come to Lambda, when they join Lambda, or when we speak with deep learning researchers at other companies, and then they understand how intricately linked hardware is to software development, and like how much of a performance gain they can get, they quickly realize that, wow, they can go from a 1x performance speed to a 4x or 3x performance speed by doing almost no change in their code, and not spending months and months on figuring out how to change your code, just by changing some sort of hardware, some sort of, for example, let me speak in specific example, right? Like if you're using, for example, a 3080 GPU right now, which is in the market, MSR, I'm talking about MSRP, it's like a $700 or $800 GPU. And going to, let's say, 3090, or let's talk about A6000, going to an A6000 improves your performance by 3x. Now, A6000 is like I forget, but like a $4,000 card. So now you're spending almost 5x the amount. But let's say it's increasing your speed. Like for example, for a language model, I know A6000 is like increases your speed to 2 to 3x the 3080 model. So like let's say it's increasing that speed by that much amount. I know that, yeah, you're paying 5x, but your speed is increased by 3x. A lot of engineering teams would be willing to pay that differential, because it has just saved them months and months of time on optimizing their code to get that to run 5x the speed on 3080. They'll be like, just by changing the GPU, they've been able to increase that speed and save a lot of time. So if it makes sense for them, they would do that. But I've also seen teams where they're just like, nah, why should I spend 5x when I'm only getting a 2x or 3x increase in speed? Let me just add more GPUs of 3080s in their cluster. And if that works for you for your model, that's well and good. But just remember, there is cost that comes with adding more nodes. There is more power usage. There's more networking that needs to be figured out, and your model gets more and more complicated as you spread it out across more nodes. So there's always a pros and cons in terms of how you are structuring or how you're thinking about increasing your kind of models and increasing your infrastructure. So these are the things and parameters that you need to consider, and it really depends. Again, it comes back to the rule number one, and the only rule is know your ML team / application. Just knowing that will help you figure out the best kind of cost structure, whether that may be on cloud or your on-prem setup, and as well as cost plus as well as optimization of your model. And personally, I found it's like a huge joy to see that what model used to take me like freaking 7 days to run, now I'm running in 2 days. Like, even if I have no commercial application for that, it's just such a great thing, because now I can change my model a lot faster. I can do more trial and errors and just have that set up more easily. Quickly, I think, as I mentioned, these are some of the terms that are good to know about PCI topology. As I mentioned, how the GPU communicate with each other. I'll quickly go through this in terms of diagrams and how this is in real world.
One moment. There was a question from Carl Anderson. He said, heard NVIDIA's chief architecture AI systems talking about NVIDIA's Selene supercomputer built on the NVIDIA DGX SuperPod reference architecture. He mentioned about rewiring time, reconfiguring the racks. Does that occur often, or is it more of a research and top of the line systems?
Generally, there are two things that I've seen personally. One is people building on architecture, like people starting with 1 or 2 nodes and then building on top of it as you go along. And then another is people just buying fully designed clusters. So the second part, in that there is no rewiring or restructuring. People have already designed this, like, for example, Selene, that's state of, if you're talking about state of the art, that's the best in the world out there. And then the DGX solution with, with the A100s and the InfiniBand, it can support 1600 Gbps total networking bandwidth in terms of IB. That kind of design requires a lot of frontal thinking to design Selene. Like, I guarantee you, NVIDIA did not just start building up a rack and then just added more rack as they went along. They designed the whole system first and then they racked it. So no rewiring needed. But you and I, or most companies or most startups, can't start with Selene and have that huge amount of setup. What they are starting out mostly is with 1 or 2 nodes with A100 or A6000 or T4s for if you're doing inference, kind of setup, and then they're adding more to it. And within that, absolutely, you will see, rewiring. Because, for example, initially, as I said, you started with A6000s for just doing your hyperparameter search, right? Now you're going into production. Now you realize, hey, actually, I need A100. I need that networking bandwidth to improve it. And I need InfiniBand. So before, when you started, you didn't have InfiniBand switch. You didn't have 100 gig cards in your server. You didn't have any kind of configuration. But now you're going to A100 servers. You need all this setup. So either you just give up on your old servers in the sense that, okay, I'm not going to bring this as part of my new cluster and I'm going to design a new cluster. Or if you want it as part of your new cluster, you're now basically saying, okay, I need to go put in a Mellanox card in my old server. I need to do a full kind of networking design. So there you need a redesign. And we personally at Lambda, and this is from my personal experience, we definitely see a lot of our existing customers, as they build upon a rack and their setup, even going from workstations to servers, designing their networking, we see like they require support services where they're like, if they don't have internal infrastructure admin setup, they require support services from us saying, hey, can you please help, kind of bringing your existing cluster and new cluster all together. A lot of time, these companies have their own infrastructure administration folks who are very, very talented and who figure out, okay, how I'm going to combine this two, how I'm going to make the storage work with the new setup and everything like that. So the answer is twofold. Yeah, if you're predetermining everything, absolutely, we see very little rewiring there. But if you're just building up, we do see a lot of kind of ad hoc additions to your server setup. And that's where, having someone who understands it can help a lot, because they can ask you a question like, someone can ask you a question, okay, how many GPUs are you planning to scale it? 16, 48, 64, what is it? If they say, okay, 64 GPUs, then okay, that person's looking for 8 nodes. Like, for example, if you're designing a DGX A100 solution there, or a Lambda A100 solution, which can support 8 InfiniBand cards per node, you need at least 64 ports. And that's just at least, you factor in the topology, redundancy topology, fat tree, all these networking terms networking topology switches. And then you need a lot more ports. So you need 3 switches there. And it's better to do it beforehand than adding it on later. even if you buy 4 servers right now and 4 servers later, because designing that network can be very time consuming. So hopefully that answers it in terms of, from my personal experience. Different people have different answers, but someone who's designed Selene, they would know, that's a fantastic system actually that's designed, and they would know that if you're designing from scratch, it's easier to design it when you think about the whole system that you want to build than actually adding it ad hoc as you build upon a cluster. Oh, and I didn't include NVIDIA, of course, here, but by the way, NVIDIA is a huge resource for all of the GPU benchmarks and everything like that. But yeah, quickly, as I said, I think I'm going to cover some of the topology here. Let me see which one I like the most. So by the way, these diagrams are PCIe topology, or just think of this as connection links between GPU communicating with either the CPU and memory and external networking and storage. So so when you're buying a solution, right, it's very kind of especially within deep learning, GPU to GPU communications matters a lot. NVIDIA stresses like, why is A100 a really good GPU? Other than, of course, the big compute speed, is because of its ability to do GPU to GPU intercommunication at extremely high speeds. When you're talking about NVLink, NVSwitch, you're talking about 1600 or 900, sorry, I forget exactly, but even if we say 900 gigabytes per second GPU to GPU communication speed, I mean, you're never going to be bottlenecked on GPU to GPU intercommunication unless you're doing some kind of crazy language processing model. But usually how GPUs communicate with each other is something called PCIe lanes. They communicate by PCIe lanes, and these are connected via either PLX switches or directly through CPUs. The PCIe lanes nowadays, we are on generation 4 of this PCIe lanes. They basically have I believe 32 gigabyte per second intercommunication speed, and that's plenty for most models. Like, for example, if you're doing ImageNets or a lot of image models or CNNs, 32 gigabyte per second PCIe lane intercommunication setup is more than adequate. And that's what most of your GPUs, like the 3080s, the 3090s, and the A6000s, these are called PCIe GPUs. This is the communication lane that they are using to communicate between the GPU to GPU. So when you go multiple GPU models, these are, you basically have your data coming in from your storage to most likely the CPU to these GPUs. And then, you're running your model on multiple GPUs and it's doing parameter optimization. And their GPUs just talk to each other. They don't go through CPU. They will just talk to each other via PCIe lanes or PLX switch. Where they're just optimizing for the different rates, or they're converging upon a solution, they're averaging a solution when the model is run. And that's where, again, NVIDIA, what they've done is distinction between, like, for example, an A6000 GPU, which is an enterprise GPU, there the GPUs can communicate with each other directly, like there's peering enabled. But with something like a consumer GPU, like a 3080 or 3090, NVIDIA has disabled this peering, and most likely on purpose to create like a kind of layering of GPU layered, but they have disabled this peering. So the GPUs now have to communicate via CPUs rather than GPU to GPU. So again, for image models, it doesn't really matter because you're not really bottlenecked on, you're not really bottlenecked on latency as much or on the interdependency between GPUs. But on language models, for example, it really matters how the GPUs are communicating to each other. So there it matters whether, it can affect, I have seen personally like a 10 to 20% performance differential between using like an enterprise GPU like an A6000 or 3080 just because of how the networking topology is. But just some of this like topology diagrams that I've drawn here, these are or like used or found on internet, basically are basically, this is like a workstation topology. You can see I can fit 4 GPUs in a single workstation. So you can see GPU 0, GPU 1, GPU 2, GPU 3, and how they're communicating with each other. This is more like a server topology, like 8 GPUs in a single rack box kind of setup with 2 CPUs. And even within that, there are multiple types. So there's like a dual root topology, which is like 2 CPUs talking to 4 GPUs each, or there is a single CPU talking to 8 GPUs altogether. It just depends on whether your applications are compute intensive or GPU intensive, kind of what type of setup that you use. This is the NVLink. So this is the high end. Greg mentioned the DGX, or Lambda has the Lambda Hyperplane A100 or V100 setups. These are amazing designs that NVIDIA has come up with, where they say that, okay, we are going to bypass the PCIe lanes. And they called it NVLink, their own kind of proprietary. And I'm not on silicon infrastructure side. I'm not sure how they design it. Maybe it's similar to PCI lanes, but they have achieved amazing bandwidth, almost 10 to 15x to 20x the speed of PCI lanes in terms of GPU to GPU communication. They use specific types of GPUs called SXM format for this. They don't use your A6000s. Like, for example, an A6000 or 3090 cannot do this. Only a V100 or A100 GPU can do this type of communication bandwidth. But as you can see, they have just basically have multiple lanes from each GPU to all the GPU. It's an all-to-all communication. So, for example, in here, if your GPU 0 wants to talk to GPU 7, it has to go through different layers, either through CPU or go through the PLX switch and run across. Whereas in an NVLink NVSwitch topology, the GPUs are all interlinked, all to all. So like a GPU 0 can communicate with GPU 7 directly. It doesn't have to go through any switches or any CPU or anything like that. Again, leading to huge increases or huge reduction in latency. Similarly, these also allow for direct storage feeding into GPUs, direct networking feeding into GPUs. So this is why I again emphasize on know your models, know your ML team applications. If your requirement is low in latency, high, direct communication with GPU, these are the GPUs, these are the server architectures you need to go with to maximize. Otherwise, if you're running large-scale distributed training network, and if you do not have an A100 setup, you are leaving a lot on table in terms of optimization. You're really kind of limiting if you're using like an A6000, or if you're using like a consumer card, which NVIDIA wouldn't even allow in a server setup, but you're leaving a lot on table in terms of optimization and in terms of performance increase because of all of this kind of bells and whistles that this kind of topology provides. Again, I didn't want to go into too. Go ahead.
A question from Velas in the audience. Why are language models more bottlenecked than vision models by inter-GPU communication speed? Just a question about that.
Yeah, sorry, I've been saying that a lot, but so this is more of a generalization. Of course, you can find exceptions, but language models are more bottlenecked. So there is a lot of data. Like, language models are bigger. As when you like run NLP models, you'll see that the batch sizes are larger. Like, for example, I remember like BERT large, the batch size is like 24 gigs there. Like, you can't even fit a BERT large single batch onto like a 3080 or 3070, for example. You need like a RTX A6000 with 48 GB memory. So you have large batch sizes. So what that means is that there's huge amounts of data flow that is going from storage to GPUs. When you have huge amounts of data flow, that automatically means that, because you're processing huge amounts of text and you're processing huge amounts of data. So the GPU compute is processing huge amounts of this data, and you want the data not to be a bottleneck. You want the GPU compute to be a bottleneck. So you want to process as much data as possible. And if you have high networking and high bandwidth communication between the GPUs, it means that GPUs can talk to each other that much faster with as much low latency. So the data is flowing way faster than the data is flowing as fast as it can, so the GPU is the bottleneck. And why is this important in language models? Is because language models utilize huge amounts of data there, and they process huge amounts of data more quickly than image models do. So that's why you need a lot more networking interdependency for language models. I don't mean to say that computer vision models don't require it. There are absolutely GANs and there are models which require high amounts of networking bandwidth. But within language models, there are models like ImageNet models or YOLO 3 or YOLO 4. You're not as much bottlenecked on networking there because there is not as much amount of data that is being transferred, not as many amount of weights or parameters in a language model, sorry, in a vision model that are being communicated from GPU to GPU. So you don't need, so your GPUs are not bottlenecked. They're not waiting for another GPU to receive the data and do the calculations and then converge it back to do the average kind of weights. Whereas in language model, because of the amount of data, they are waiting on that. So this is why the GPU to GPU intercommunication is way more important in personally than we have seen in language models than in vision. But I want to be very clear, there are lots of vision models where it is important. It's just that for language model, it's more of a general statement, whereas for vision models, it depends on the type of model. Like, GPT-3, for example, or Microsoft's, what their Google's research, the Google search engine team do. These are all language models or some version of language models. They're transformers or they're translation models. These are all high bandwidth, high communication intensive models. Hopefully that has answered that and I've not rambled on too much. There are lots of articles about this. Mm-hmm.
I just said, Vila says thank you.
Okay, awesome. Okay, yeah, so these are kind of the topologies that you need to, just even knowing the term, like, for example, a lot of people hear when NVIDIA markets NVLink, NVSwitch, but just what is it truly, right? Like, what does it give you? It gives you this, it gives you this all-to-all GPU communication, with not only within GPU to GPU, but direct from storage, direct from InfiniBand. So when Lambda designs an A100 system or NVIDIA designs their own A100 system, this is what is being provided when we say that it comes with NVSwitch, NVLink, is you're getting that, and that can be very useful for models. So just knowing these kind of things can be, can give you 20%, 50%, 2x, 3x boost in your kind of model training parameters. I've already covered this, like shown this image before. I just wanted to show again. These are real life examples, like when Lambda designs its motherboard and when Lambda designs its servers or works with, manufacturers out there, we kind of design. So you can see that this is for example, a dual CPU server with 8 GPUs available plus networking NIC. So you can see there are the 2 CPUs where you see the AMD EPYC. They're all connected by the DIMMs, the memory slots, your RAM, and it has total of 32 kind of DIMM slots, and they're directly connected to the CPUs. So if you have a storage with, and then there are like the NVMe drives within the server. So when the storage is within the server, how the data flows goes from storage to random access memory like RAM, and then, it goes to CPU, then RAM, and then I think it goes where it sits while it's being called upon. And then then goes into the GPU. So this is kind of the network topology, or sorry, not network, the PCI topology that is present in a server architecture. You have your networking ports and everything all interconnected via CPU to your GPUs, and this is how a single server kind of is connected to each other. And this is the A100. Lambda has its A100 setup, and which is it's called the Hyperplane A100 and 8X A100, or it's the same thing as the DGX A100. This is where you have the CPUs, the dual compute, the CPUs, and everything like that. But what it changes is there's this NVSwitch layer or fabric, as NVIDIA calls it, which connects all the GPUs directly to each other, so they don't have to go through CPU to talk to each other, and also the InfiniBand NICs and everything, which are all connected directly by PCIe lanes to the GPUs, allowing for networking to come directly into the GPUs, again, bypassing CPUs and RAM and storage and everything like that. So very interesting design. I'm pretty sure NVIDIA is going towards kind of like, they just wanted to utilize GPU and networking and storage. They just bought Mellanox recently. That's kind of the goal, is to bring networking and GPU, everything in-house, doing the RDMA, all in-house, kind of, they're being smart. They're like rethinking the design. They think that, which for deep learning is very useful. because CPUs are not really needed for deep learning. So they're rethinking that whole design of servers. They think that you don't need CPU compute, you don't need a bunch of RAM, you don't need a bunch of local drives. You basically have your external storage, you have your GPUs, you have your InfiniBand, and you have your NV switch, and that's it. You just add GPU nodes, you have your head node, and you just scale up on GPUs as much as you want. It's very interesting thinking. That's how it's going to be.
Quick question from Carl Anderson. Just wanted to find out about your slides. Could you post them after the fact on the Meetup site? There's usually a discussion section. You can just put a link there. People would be interested in the slides.
Thank you. Yeah, let me discuss it internally. I will definitely, let me kind of clean it out for public sharing, and I'll definitely post it on that. Okay, finally pulling it all together, I promise this is the end. Basically, designing a cluster is an interesting exercise if you are not into it, like if you're basically not in, if you're not in a position, or your setup or doesn't require a cluster, it's just interesting to know. But if you do, then it's very, very interesting to learn kind of all of these things that I've covered, write your own cluster rack, build up materials, as I said, it comes with a lot of external aspects, power, co-location, everything like that, software, all of us companies, made by NVIDIA, Lambda, NVIDIA is a leader in this space, and we all try to design software setup and everything so that it makes it easier to design your own on-premise cluster rather than and make it as close to like a cloud use cases as possible. Because again, on-premise is more cost-effective than cloud, but it depends on the application. Sometimes cloud can be very cost-effective too, as I mentioned in the beginning, for your inference use case, scaling up to 100,000 users and back down to 10,000 users. So it really depends on application.
A question for you on cost. So if I'm making a pitch to executives above me to purchase something, let's say I don't have the huge user base of some web app that goes widely up and down. I've got a department of people just training image models.
Yep.
So what is a common break even between cloud costs and GPU costs? As far as if you think of over a year, your GPUs are X% utilized, what's a percentage that the cloud may become more practical?
That's a very, very good question. That's a very practical question, first of all. Second of all, I'll give a general answer. And finally, on Lambda's blog post, there is a blog that we have published which does like a TCO, a total cost of ownership analysis. And let me be upfront. You can always find flaws and you can always find some miscalculations in this kind of things. Depending on where you are, your co-location cost might be different. What you might think as admin support cost might be different, but it gives you a pretty good total cost of ownership analysis. So do go on Lambda blogs and kind of take a read. Let me answer the question specifically there. Depending on the utilization, let's say you are doing let's say your use case is 50% GPU utilization, right? At a 50% GPU utilization, designing an on-prem cluster will be kind of the return time for it will be anywhere from, depending on the GPUs you choose, either if you're choosing A6000s or A100s or V100s, whatever it is, it can range anywhere from 6 months to 14 to 15 months of return on investment. But do note that putting an on-prem cluster, especially for training, comes with an upfront CapEx. So that's the pro and con. Like your executives, when you're discussing within a company, both from business side and engineering side, having an on-prem cluster is, if your use case requires you that, okay, I'm going to be utilizing this cluster for next 2-3 years, on-prem is generally going to be cost effective. What I'm not saying though is that on-prem is not always, ease of use effect. It will depend on exactly where you get it set up. If you just buy a bunch of servers and just rack them up, and if that's your use case, that works perfectly fine. If you put in software and if you know how to manage it, that is even better. But including all the cost, in just terms of cost, you see a return time of anywhere from 6 months to 15 months is what we have noticed, as opposed to running it on cloud. Now, Lambda does offer cloud solutions, and we try to bring it as closer to reality as possible. But, unfortunately, that's how the pricing structure is in terms of, because cloud does have overhead in terms of what it's charging you than running your own on-prem setup. So that's kind of the general rule of thumb that I would give for a return on investment or total cost of ownership analysis of your own TCO of owning your own hardware. If nothing else, they have depreciation. So your accounting will appreciate it. They will have depreciation schedule of 3 years. So you get some cost back from that setup. And then finally, because depreciation is 3 years, but not only because of that, from engineering perspective, this cluster, NVIDIA has a really good GPU cycle, I believe. They have a just Moore's law, which kind of, I don't know if you're exactly following it, but NVIDIA's own law, whatever it is, their internal law, they follow a really good structure. They redesigned their architecture to have a good compute increase every 2.5 to 3 years. So, and the good thing is this, their old architectures don't go bad, don't go bad in the sense, like V100s are still valid, very, very good GPUs, still very fast. A100s are going to last for another 3 years. Whatever their next will be another 3 years. So even if at minimum you're using these clusters for 3 years, at maximum, hey, these are just running and running for years on end. I mean, you go to AWS, they're still running K80 instances. I forget, like those are 80-year-old instances. Those are already been deprecated. AWS is still just making money on this, and it's fantastic business for them because they have been paid for long ago for that. So this GPU has just run a long time in terms of setup and architecture. So yeah, as I said, finally, putting it all together requires a lot of thoughts. If you have a good infrastructure team and if you have experience within that, it can definitely be done internally, or again, a pitch to Lambda. Lambda specializes in this. We pride ourselves on, especially within the field of deep learning, machine learning, and I think you mentioned there's folks from NVIDIA there. They're also they know a lot about this too. But basically, Lambda's kind of value add comes from providing all this expertise and setting that up. So if you'd like to reach out and set up a call, please do reach out, and we would be happy to kind of chat there.
Audience question from Close Lead. Question: when moving from an on-prem cluster to a cloud, how do you determine a good host/approach or a break-even analysis?
Yeah, the first and foremost thing, and I'll keep it on the slide, just it's a slide, but the first and foremost thing is on the software side, whoever asked that question, going from on-prem to production or cloud, please make sure your environments match. Otherwise, it's going to be a terrible experience for your end users, whoever are using your cloud and your engineering team. Second of all, in terms of holistically thinking how to scale in terms of cost, it really, so we have customers, and I have personally seen this, in terms of hardware or appliance side, if you're thinking about this, what people do is, they will plan out, if they want to continue on premise, they will plan out their inference or production setup way in advance, and then place the orders, and then that's easier. But when you're transferring, when you're doing data egress from, basically from your on-prem to cloud, there are a few ways. If you're in co-location, there are direct uplinks from your cluster or your co-location facility into things such as AWS or GCP or Microsoft Azure, and they utilize this. In terms of cost, it's really hard to say for me, honestly, because for production TCOs, it really depends on use case. As I mentioned, if you have a very, very uniformly predictable use case, I'm trying to think, like, if you're running, for example, I don't know, like maybe like an image model, which is in, you have 100 stores, that's it. You're running the feed from those 100 stores onto cloud, and you're doing an inference on those things, and it's 100 stores. then you can build it on-prem and the same analysis will stay. Like it's 6 to 14 months of TCO to pay back a return on investment as opposed to cloud. What you'll spend on cloud in 14 months, that's the amount of money you'll need to build a cluster like that. But if your user base is like constantly fluctuating, like Netflix's does, and you need high uptime. Oh yeah, I forgot about this. You need high uptime, high latency. Your use case is spread out across the United States or across the world. It matters to you that, then absolutely no other solution than cloud there. You forget about TCO there. If your customer has to wait, if your data center is in Texas and if your customer is in Germany and they have to wait, you're going to lose that customer. So you need the cloud setup there to do that. And secondarily, if you want to be sure about, with AWS, you get your peace of mind, for example, that they have backup, they have backup to backup, they have backup to backup power supply. It's high uptime, they're 5 nines of uptime. Whereas if you're designing your own cluster, unless you're designing in a really good co-location and they have promised you 5 nines of uptime, if you're just putting it in your own cluster or in your server closet, that's a risk that you're taking there. So yeah, so those are kind of the parameters that you need to consider.
And one other question from Dave. Why don't special purpose AI accelerators have a better price performance ratio than GPUs for neural net training? Or is that not true? And I might add to it myself, if that's your business, I imagine you guys like check into other accelerators periodically.
Yeah, I was thinking really hard whether to add that slide or not. By the way, yes, absolutely. There are now new AI accelerators coming out. There's a few names. Of course, there's AMD's GPUs. There's Habana. There is Tenstorrent. There's Grok. There is GraphCore. And the answer is more complicated, that they are not as fast as GPUs, NVIDIA GPUs. They, in some use cases, they are as fast, or they can even outperform this. But one of the biggest things I'll say, and I have to give credit to NVIDIA here, is their software setup and stack is just so uniform and just runs so well, and it's so well supported. And the vision they had, way back when they realized that GPUs are going to be used for deep learning, and however they stumbled upon it, I don't know their internal story, but they designed that, and you can use it across the board. So when you are thinking about designing a cluster right now, I'll say like most of the time you're using NVIDIA's GPUs. The accelerators, yeah, I mean, I have seen the use cases for GraphCore, really great at some type of models, and I've seen them being really great at Monte Carlo simulations because of the architecture there. But if you're talking about in generality, even they will agree that their software is still in the build process to support all of PyTorch applications, all of TensorFlow applications. Other accelerators like,
what about like Google TPU? Because that would be supported by.
Yeah, sorry. Yeah, Google TPU is great. Google TPU is a really good, I mean, it supports TensorFlow and TensorFlow only, I think right now. I think they're working on PyTorch, I'm not sure. But the two things with Google is one is their price to their flops per dollar is pretty great because Google provides it at a pretty good price. So if you're on GCP, that's pretty good. But by that logic exactly, you can only kind of get them on GCP. They don't sell those TPUs. So you can't design an on-prem cluster. Of course, they're not on AWS, as far as I'm aware, or Azure. So you are restricted to there. In terms of use case, TPUs do have a way more software support. I haven't personally ran code on it, so I don't exactly know what the performance benchmarks are against like GPUs. I'm assuming the GPUs are faster, but if you do performance per dollar, they might be up there with the NVIDIA GPUs. But again, when you're talking about scaling, like NVIDIA GPUs, for example, memory, right? Like A100, 40 gigs of memory. Oh no, sorry, the new A100, 80 gigs of memory on them. I mean, that's brilliant for some of the models out there. So, that's where the A100 GPUs will really shine through. So NVIDIA has done really well to maintain, to being a market leader. Not to say the Google TPUs, for example, is definitely a good example of an alternate provider. And just be on the watch out for this space. In the next year, you will see so many AI, specifically AI accelerators coming out, and more and more accelerators with regards to application specific. I know, for example, certain accelerator company, and I'm under NDA, but basically, they're designed for finance application. The models that run in the financial industry, and NVIDIA will have to be on its kind of toes to make sure that their GPUs perform as well as they do, because NVIDIA knows this. It's the reality of the market. They will get competition. AMD has launched ROCm. It's getting better and better. PyTorch just literally a week ago announced support for ROCm. So people are going to start testing it out. People are going to release open source software there, and competition is going to come through. So it's just who takes the first plunge, who does the research. Right now, like if I'm running a company, I'm going to go with NVIDIA because, hey, I'm not into designing software support for these AI accelerators. I'm into running my own machine learning model on this AI GPUs. So I don't have the engineering resources to design that and to maintain that. But as these get more mature, as these companies who are providing these accelerators come out with better software support, then yeah, absolutely. And if it's as easy as if I have my PyTorch code on NVIDIA GPU, and if I just take it to AMD or AI accelerator or TPU, if it's just literally without making any change to the code, if that's that easy, then then it becomes a pure kind of setup between, okay, who is providing me the best performance at best dollar value? That's where I'm going to go. But we are not there yet in terms of this, in terms of the setup.
Another question from Dave. How much storage fits in a 2U flash storage server?
NVMe, gosh, literally just this year, there has been a 24 drive 2U storage server that has been launched. And if you're talking about NVMe drives, there is an NVMe drive which can support, each NVMe drive can support 32 terabytes. So you can do the math, 32 times 24, and then whatever RAID configuration or ZFS or whatever spectrum scale, whatever configuration you choose, you can figure out the thing. But of course, 32 terabyte NVMe is almost impractical unless you are an oil and gas company and have that much money. It doesn't, the costing doesn't scale practically. So until the point where the prices scale practically, NVMe, like a 15 terabyte NVMe drive is a very good storage price point. So I would say right now, in terms of practical use case, 24 times 15, which is what, 360 terabytes or 368, because it's a 15.68 terabyte drive. So 368 terabytes or so of raw space on a 2U server in a NVMe setup is feasible. So yeah, high amounts of storage.
Sounds good. Any other questions from the audience? There's been a lot of Q&A going on, but I'll just wait. Okay. Did you have many other slides to cover? Are you pretty much wrapped up?
No, I'm pretty much wrapped up. Just want to thank everyone, and especially want to, again, Lambda is a great resource. I'm not just advertising Lambda. NVIDIA is also a great resource, but Lambda has great blogs. As I said, RML, Hacker News, feel free to explore those. These are awesome use cases. My citations belong there. I know I've gotten a lot of resources there. These are always great things. A lot of great talks from Lambda, NVIDIA. Great research team talks from Uber, Google. Absolutely use cases. Just explore this world. It's fantastic. And trust me on this. Hardware can bring a huge amounts of optimization into your if you're running a company or if you're running this team, and if your team has this prerogative that I want to increase the speed, right now it's taking me 1 day and I want to bring it down to 6 hours, I guarantee you, unless you're already using A100s or stuff like that, I guarantee you there is a hardware solution out there which will help you reduce that at some cost, of course, but you'll just have to do a cost to time parameter analysis there. Again, about Lambda quickly, we provide AI infrastructure. We also provide AI services and software consulting. Most of us work in ML deep learning space. So as I said, Greg mentioned the kind of high resolution setup, and we are working in consulting capacity there, where we actually write the models and we actually optimize models for end users. That's where we also shine against some other vendors out there. Not only do we have understanding of hardware on-premise appliance, We also provide consulting. We also write models. We have optimized models. We also provide consulting on cluster side and everything. So please check us out, and look at the white paper Echelon. It's a really good white paper, just for knowledge sake. And yeah, thank you everyone for attending. It's definitely a pleasure to share. And I think I talk a lot sometimes, but it's just because I'm excited for this field and kind of where it's going. It's a huge space. I think NVIDIA themselves say that the market cap of AI space is going to grow 10x. So not only good for my company, but I'm hoping anyone who's in this space, great for your future prospects as well as companies that you run.
Well, thank you very much. I appreciate it.
Thank you.
So, thank you.
Thank you. We're good to log off.
Yeah, we're good.